We are really pleased to be here today, and we thank you very much for this opportunity to get together and celebrate this event. And Daniel, thank you very much. We've had tremendous support from Queen's over the years, as we have from our other Canadian institutions. And I'd like to point out to begin with that there's fortunately a very large representation of my colleagues here and their spouses who are an important part of this whole thing. And I'd like to first of all point out that George Ewan from Queen's University was our founder in Canada, along with Herb Chen from University of California at Irvine, that joined the project and really had a seminal idea in the very beginning, as did George, in terms of where we could do it. Dave Sinclair was the first UK spokesman for the project, and now has returned to Canada and was the director, which he was the person who created SNOLAB, which is now a permanent, long-term international laboratory with the same sort of low radioactivity characteristics that we were able to take such good advantage of with SNO. We have representatives from the United States who were our spokesman, Hamish Robertson and Jean Beyer. And we have our people who have been successors to Dave as spokespersons in the UK, Dave Wark and Nick Chelly and Steve Biller. And we have many others who contributed so much to the success of this project. And I'm just so pleased to be here with them, together with you, in terms of celebrating this recognition that we are very grateful to the Royal Swedish Academy of Sciences and the Nobel Foundation for. So it's wonderful to have this gathering where I get called upon in these circumstances to try to explain what we actually did, which is never easy. But I'm here in Sweden, and I feel very comfortable for a number of reasons. Sweden, I was just having a conversation with one of my heroes, Boreas Holming, who was captain of the Toronto Maple Leafs for many years, and a team that I've followed since I was a kid, listening to hockey on the radio in the 1950s. And we were talking about the similarities between Canada and Sweden, similarity in climate, similarity in approach to life, we think. And so I was kind of inspired to try to come up with a hockey analogy with how neutrinos change their flavor, which is something that in Canada apparently is understood by the use of little donuts called Timbits, but that wouldn't go over here. But you might recognize that it is typically Canadian, because Tim stands for Tim Horton, who was a defenseman with the Toronto Maple Leafs, as was Boreas Holming for many years. So hockey pervades both countries' approach to life, it seems. Okay, so imagine that we have a tremendous goalie like Henrik Lundqvist, who's starring for the New York Rangers right now. Imagine we have a stellar defenseman like Boreas Holming protecting the net, and let's imagine that we have a forward like Matt Sundin, perhaps, about to shoot the puck. Well, it turns out that in large-scale things the size of a hockey puck, this doesn't work. But for tiny particles like neutrinos, it actually is possible for particles to change from one type to the other. It turns out that if they were to make such a change, then by the time they strike the net, you can only propose or calculate a probability for whether or not they're going to be one type of particle or another, as seen by the goalie. And it turns out that actually, if it were to be the case for hockey pucks, the sort of situation we found was as though the hockey puck heading for the goalie 33% of the time continues to look like a hockey puck, but the remaining 2/3 of the time it ends up looking like perhaps something fast moving, but about the size of a peanut. Two flavors, salted or plain. Very difficult for the goalie to stop, as you can imagine. So it turns out for many years, all it was, the only statistics that were kept were the save percentages for goalies who were trying to stop these particular types of pucks. And they were turning out to be only about 1/3 the normal 90% or so that goalies are able to work out. But it turns out that we had a real advantage in Canada. We had a material called heavy water, and that enabled us to do something further with neutrinos. And it's as though we had a very high resolution, high speed goalie cam right behind the goalie, looking at everything that's coming at the net. And that camera was capable of observing those peanuts as well as observing the hockey pucks themselves. And so we could, with our measurement, be able to tell all of the shots that were going on the net, which is the equivalent in the case of neutrinos from the sun, of determining all of the neutrinos that were produced in the sun. And what we observed, in fact, by comparing the number of saves, the number of things that were actually pucks with the total number, we were able to clearly show 1/3 hockey pucks, 2/3 peanuts of one flavor or another. That was quite revolutionary because it turns out this process of changing within quantum mechanics is something that can only happen if neutrinos have a finite mass. That's very important because it goes beyond the very successful standard model that has been tested at CERN and elsewhere and works in other circumstances. We're hopeful that understanding this is something that will enable us to describe the universe more completely by going beyond the standard model and working out how it is that neutrinos end up augmenting that standard model. So, but it happens, in fact, that in the sun there's another process that takes place. Normally, it depends on how long the neutrino travels in terms of determining those percentages, that 1/3 to 2/3. But in the case of the sun, if the neutrino happens to hit something much more massive, in this case an electron, it's about more than 1,000,000 times more massive, kind of like a very solid defenseman like Salmi. So if in fact the neutrino hit, or the hockey puck hit the defenseman and bounced off, it fixes permanently the ratio, and it stays in that ratio all the way from the sun to our detectors on Earth. So a defenseman is a very important part of what we measure, as it turns out. But in addition to that, we understood now how the sun burns, because by measuring the total number of neutrinos, we're able to measure very effectively the fusion power source that exists in the core of the sun. We also know properties of neutrinos that help us to learn how they influenced how the stars and galaxies formed in the early universe. We know now that neutrinos are the things that continue to make supernova explode, collapsing stars explode, and it turns out that all of the elements heavier than iron are made in those stars. So in terms of our very existence, we know things as a result of understanding neutrinos. But we also know that the calculations of a basic physics nature that are used to calculate the sun are very accurate. And those are the same calculations that people are attempting to use to understand nuclear fusion here on Earth, as they try to confine that very hot process with magnetic fields rather than the gravity as happens in the sun. So it's an example of how knowing basic physics very well, or basic science in general very well, enables you to then approach applied topics with confidence in your calculations and to be innovative in those circumstances. And that's what we're trying to do with these basic science projects. So we've been very fortunate in being well supported in all of our countries to do this research, and I've been very fortunate to have such a fantastic, talented group of collaborators to work with over many years. So thank you to them, thank you to you. It's a real pleasure to be here.
Thank you.